Good. After setting up the basic idea of a multiscale analysis, we arrived at this form for the function phi of x and y and t, and split it up into a slowly varying carrier wave, envelope function and a fast varying carrying wave. And if you do the simulations of this equation, it's actually pretty easy to do. You would see this explicitly, that there's this distinction between slowly varying amplitude and fast carrier wave. So now let's rewrite the Swift-Holmberg equation. So the Swift-Holmberg equation in the multiscale analysis. Since we have introduced slow and fast variables, we can now also rewrite our differential operators dt by the chain rule, because I'm considering lowercase t twiddle and uppercase t as independent variables. So I can rewrite the derivative with respect to t as a sum of derivatives with respect to t twiddle and t. And for the second one, I need to use the chain rule. So this is then epsilon squared dt. And I do the same for x and y. So dx is the derivative with respect to the fast variable plus epsilon derivative with respect to the slow variable. And for dy, this is the fast variable plus the square root of epsilon derivative with respect to the slow variable. And now we have everything in place. Everything is nicely expanded out in orders of epsilon. So I insert all of that into the Swift-Holmberg equation, where we would like to have, one thing I need more, there's no dependence on t twiddle and also y. Because of our assumptions, we have assumed that we have a stationary carrier wave in x direction. So there's no y variable involved, and there's also no time involved. That's why we do not have any dependence on that. And that means then if we want to translate our derivatives, the dt is simply turning into epsilon squared dt. Then the other operator in the Swift-Holmberg equation is the one that contains the Laplacian squared. So, and as you insert all of that, you get dx tilde squared plus qc squared squared. That's coming from the fast variable giving rise to the carrier wave and our order 1 wave vector qc. And then I'm now ordering all the other terms according to our bookkeeping parameter epsilon. So I'm getting x twiddle squared plus qc squared. It's a bit of algebra, but not difficult, just a lot of writing. dx plus d squared y. Okay. So just expanding out the operator, inserting the expansion that you have in the top line. That's what I'm doing here. That's to linear order and to quadratic order. In our bookkeeping parameter, there is epsilon squared times 2 times, dx twiddle squared plus qc squared d capital X squared plus epsilon squared 2 dx twiddle dx plus dy squared square. So I hope I got it all right. And then the other terms are of order epsilon to the third. Okay, you just have to write it out. Like in all perturbation theories, there's a bit of algebra that's involved. And now you have these operators, and what you do is you just insert it, here it is, in this Swift-Holmberg equation. That's all you do. And as you insert it in, you compare order by order what you do get. What we also do is we write the phi also consistently as epsilon phi 1 plus epsilon squared phi 2 plus epsilon to the third phi 3 plus dot, dot, dot. Now, to do the analysis, I need a few abbreviations that make my writing a bit easier, but the abbreviations also have some particular meaning. I'll take one operator that I call L. That is the original operator dx squared plus qc squared. So this is dx twiddle squared. And I have another one that I call M. And this M is to dx, d capital X plus dy squared. And if you just compare my abbreviations with what you have in the middle row of equations, you see these two operators, they appear naturally in the expansions. So as we insert this in, we have epsilon squared dt phi, that's easy. That is just the left-hand side of the Swift-Holmberg equation, where I only have a dependence on the slow time scale, because the fast time scale, I took a stationary carrier wave. Then on the right-hand side, I get a term which is epsilon squared mu twiddle phi. It's again just this term. I write my mu as epsilon squared times mu twiddle. Mu twiddle is order 1. Epsilon squared is my bookkeeping parameter, and I write phi. Well, it goes on like so. Then I have minus bracket my linear operator L squared plus 2 epsilon L M plus epsilon squared 2 L dx squared plus m squared plus terms of the order epsilon to the third power phi minus phi to the third power. Right? That's what we get. Now, this is the expansion in the operators in terms of epsilon. I'll now insert the phi expansion here. So for phi, I take epsilon, phi 1, etc. The same here on the right-hand side. And then as you have all the expansions in your equations, you sort them, like in every perturbation theory. What's the order 1 term, what's the order epsilon term, what's the order epsilon squared term, etc. Okay. So the leading order term is what? So to leading order, this is of order epsilon that we have here. Well, to order epsilon, what do we have? This is epsilon squared, this is epsilon squared. Here, this is of order 1. And then I go over here. The phi starts with order epsilon. Actually, why did I start with order epsilon and not 1? Remember this simple analysis where we analyzed a carrier wave times a constant amplitude, and where we found that A scales like the square root of mu. So the amplitude is of order epsilon close to the bifurcation point. That's why I start with order epsilon here. So it means the order epsilon term is this one, phi 1, times L squared. That's the first term that we have. Okay. So order epsilon is L times phi 1 equals to 0. And we can write out again what the L is. The L was dx twiddle squared plus qc squared times phi 1. Well, and that's a simple differential equation that you can all solve. It simply has the carrier wave as a solution. There's no dependence on the slow variables. It's just depending on the fast variable x twiddle alone. So this here has a solution, phi 1 equals A times e to the I qc x plus complex conjugate. And the A still can depend on x, y, and t. This equation here doesn't inform you about the dependence of the amplitude on x, y, and z. So to lowest order, and that's something one should expect, we recover that the carrier wave is the lowest order solution. That makes sense, right? Now let's go to next order. Order epsilon squared. What do we have there? Well, we can do the counting when we have this operator L squared and multiplied with phi. There's also going to be an order epsilon squared term, not just the order epsilon term. If I take for phi the phi 2 term, sorry, there's a square here, I forgot this. There's L squared phi 2. That's the order epsilon squared term. Where else do we have order epsilon squared? Not here, because that's order epsilon to the third. Since phi starts with order epsilon, this is also epsilon squared, so not this one. What about that one? It's order epsilon here, and when I pick the order epsilon, so the leading order term from the solution, this is of order epsilon squared. Right, so we have that this is equal to minus 2L m phi 1. Okay. Well, and that's also 0 because we know that this L acting on phi 1 is 0. So here we don't really gain much, actually nothing, because for phi 2 we have the same equation as for phi 1. So this has the same solution as this one. So it's nothing that we can add here. It's just the same thing. That means we have to go a little higher in our expansion to find the non-trivial terms. So we go to order epsilon to the third. And there we get quite a few terms, because now the left-hand side matters. So we do get dt, but dt of phi 1, right? Because the phi 1 was the lowest order term in the expansion for phi. And that's equal to mu twiddle phi 1. And then let me just write it down. This is L3 phi to the third. L squared, sorry, phi to the third, phi 3 minus 2 ml phi 2 minus 2L dx squared plus m squared phi 1 minus phi 1 to the third. So what can we still use to simplify that? We can again use that L acting on phi 1 is 0. And also L acting on phi 2 is 0. So here, for example, this term here drops out. And that means to leading order, what you get is the following. You get L squared acting on phi 3. That's how I would like to write it, because I'm looking for phi 3. This is the term I want to determine. And this differential operator acting on the function phi 3 is a known function phi 1 minus m squared acting on phi 1 minus phi 1 to the third minus dt phi 1. It's all known functions, right? It's all quantities that I know of because I know this function phi 1. So this here is a right-hand side, which is basically a source term. That's why I call it a sigma. And the sigma can depend on x, y, and t also eventually. And I can work it out. I can work it out because I know the function phi 1, so I can do the calculation. So when I insert that, what I'll get, that this is then given by mu twiddle minus 2I QC d capital X plus dy squared. Those are the terms that I collect from the operator m. Then I get minus 3 times a1 squared by now inserting that phi 1 is a1 times a corresponding carrier wave minus dt And this is then acting on A1, which can be a function of time t, e to the I qc x plus something that I don't specify, e to the 3 I qc x twiddle plus complex conjugate. And there will be lots of terms in this dot, 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 where I take the third harmonic, so this one here, but we don't need it. Now let me argue in terms of physics here. So you know from mechanics, when you have an oscillator described by differential equation, and there's a right-hand side with a force, and the force is happening on the same kind of frequency as your oscillator that you have on the left-hand side, you get a resonance. Okay? So here you have such an equation. You have a differential operator acting on a function that you want to know. This has a characteristic scale QC, so internally, that's what you want to solve. And now on the right-hand side, the source term has two different contributions. One that's actually in resonance. It has the same wavelength as the one that's contained in this linear operator. And the other one, which is off resonance because it's 3 times the wavelength that's natural for the linear differential operator. Right, so here you have a resonance term. Here this is off resonance. And you want a solution for phi, and that means for phi 1, phi 2, and phi 3 that are bounded. Right? And if you want a bounded solution, you cannot take the one that will give you a resonance because that will give you a divergence. So for a bounded solution, what you must have is that the term e to the I qc x twiddle, this must be 0, because else you get resonance and therefore a unbounded solution. All right, so from that, and by the way, I mean, the way I argued here is in terms of physics. So I told you there's a resonance, and resonance give unbounded solutions. You can also argue in terms of what's called the Fredholm alternative. It's a more mathematically, more mathematical approach to say the same thing. And that's in the notes if you want to read about this. But I really prefer the physics argument here. So it means that now we have an equation for the amplitude A1 that is a function of x, y, and t. And this equation is just that this object here, this one, is equal to 0. So dtA1 equals the rescale distance from the bifurcation point times A1. I'm now don't write out the arguments, minus 3 A1 squared A1 plus 4 times the threshold, the critical wave number, dx minus I over 2 qc dy squared A1. Okay, and that has a name. This is the amplitude equation. simply because A is the envelope or amplitude for our solution. It's not the most general amplitude equation. Why not? Well, we made a particular ansatz. We assumed that the zeroth order solution is a stripe wave, e to the I qcx. So it's a amplitude equation for that ansatz, so for patterns that are stripe patterns. And now let's go back to the original variables. Which is x, y, and t, where we know the relations. So t, capital T is epsilon squared smaller t. Then you have the relations for x and y. Then the amplitude equation now is a function of x, y, and t. Has, of course, exactly the same form. It's just now that I'm done with my bookkeeping, I can get rid of the bookkeeping parameters, epsilon. They're all of the same order. This is epsilon squared and so forth. So this is then minus 3 a squared a plus 4 qc squared dx minus I 2 qc dy squared acting on A. There's some more I can do. I can rescale the equation to a form that's dimensionless. So one rescaling is kind of very trivial. I just don't like the factor 3. So I rescale A by 1 over square root of 3, just to get rid of this annoying prefactor 3. Then, when you look at the equation, here, there's a characteristic scale for the x coordinates. We have qc squared dx squared, and that means that this is the characteristic scale along the x direction, which is clear because that's what we put in. We put in a periodic wave with wave vector qc. So it's natural to rescale x such that this is qc x, and then my new variable that I have by doing so is dimensionless. And let me also add a factor of 2, because that's another convention we want to have, such that this becomes of the form which is in the literature. And we also want to have the y rescaled such that inconvenient terms that contain factors of 2 are gone. And then in this new set of variables and amplitudes, the equation has a form that you can find also in lots of publications and books. This is then dx minus I over 2 dy squared a. And that equation is again an equation named after 3 scientists. It's Newell, Whitehead, and one we know already, Segal equation. me wipe the board. Let's simplify this and reduce to one dimension. This becomes very simple. It's dTA equals mu A minus A squared A plus dx squared A. And you've seen that before. So this is what? Replace the A by your favorite symbol, like magnetization or phi. This is model A. With a standard double well potential, that's the two terms that you see here. And this is the stiffness term of model A. It's just a little bit more tricky than standard model A, because if you read it for real variables, this is fine. But the original equation, this one here, is a complex equation, right? A is a complex amplitude. It's not a real amplitude. So it's a bit different from model A. And in the literature, this is sometimes also called the time-dependent Ginzburg-Landau equation. Okay. And that's what people sometimes use as an abbreviation. And for a real variable, this is just the same as the Allen-Kahn equation, or equivalently model A that we had for the Ising ferromagnet. Yeah.
How do we choose which one of the two dimensions to keep? Like, we just kept
you not really, because by the very ansatz that we make from the beginning, we consider a plane wave in the x direction, and things are actually trivial in the other direction. And that's why keeping x is the only natural thing you can do. So what you can then do in general is not write down an amplitude equation for stripe patterns. You could also try and derive other types of amplitude equations where you make a different ansatz for your base wave, the carrier wave, because you could think maybe the carrier wave is a lattice of points instead of a stripe. And then the analysis becomes a bit more tricky in the sense more algebra, but not conceptually different. So let me recap what the essence is. So you start from the Swift-Holmberg equation, which is constructed such that it has the type 1 instability built into the dispersion relation. And then you find that an instability appears where you expect it to be. And below, above the point where the system becomes unstable, you make an ansatz into an envelope and a carrier wave. And you want to keep this whole structure, right, amplitude times carrier wave, in your perturbation theory around the critical point. And for that end, you need to introduce all these different scales because they are different order in epsilon. The carrier wave is order 1, and the small undulations is of order epsilon in one direction, and in the y direction of order square root of epsilon, and in time of order epsilon squared. And as I said, to keep all these structures maintained through the perturbation theory, you have to define those multiple scales, and then order by order go through the analysis, and that then gives you the equation for the amplitude. And this amplitude equation you can then further analyze, and that's something we'll do next time. But it is a derived equation that accounts for nonlinear effects in the vicinity of the bifurcation point. All right, questions? Yeah.
After using 1D, could we also make a guess this might be also the amplitude equation for initial wave, which preserves the rotational symmetry?
That's what I said in my answer before. So the ansatz you make with a carrier wave that's a plane wave singles out a certain pattern, a stripe. You can also make an ansatz and see whether it works that starts from a hexagonal lattice of dots, right? So it's a different type of carrier wave that you start out with. And then you say, I take this. That means you take not just one wave vector in this ring of unstable wave vectors, but 3 to get a hexagonal pattern. And then you have to do the same kind of analysis in spirit as before, just with a different 0th order 1 term. That's also possible. It's just a more tedious case. And I show you here those cases which are simpler to show on the blackboard.